We went through this example where we, from the web browser, send a request to a web server and receive that response back. And what we did is we went through the protocol stack of, okay, we start with some data. It's put inside an HTTP message, inside a TCP message, and so on. We went through that, how the data was delivered through the stack. Let's do that again, but look at in a different viewpoint. Look at a real example. We're going to go through that again, but with a piece of software instead. What I'm going to do is access a website. And at the same time, record the data that's been sent by my computer. So I'm going to, via the browser, type in a URL, press enter. As a result, my browser is going to create a HTTP message, send it through my stack, through my set of protocols inside my computer, send it across the internet, and it's going to arrive at the web server. The web server is going to take the request and hopefully send back a HTML page, and then that will be displayed on my browser. While that happens, I'm going to, on my computer, record what my computer is sending and receiving, and then we'll look at what my computer, the packets my computer has sent and received. I wanted to do this yesterday, but we couldn't get the network working. So the first thing I'm going to do, my computer is connected via the wireless LAN interface. It's got an IP address, 10.10.3.239. I'm going to tell my computer to record all of the data that is sent and received via the wireless LAN. And I have a program that will do that. It's called TCP dump. It's going to record all the TCP packets, in general, all the internet packets sent via the interface, my wireless LAN interface. And it's going to save those packets in a file, Web1, and I'm going to only look at the packets which are to and from port 80. If we remember, when our web browser accesses a web server, we use port numbers to identify applications. And port number 80 is a special number. It's the number used by almost all web servers. So if I send something to port 80, it means the data should go to the web server application. If I receive something from port 80, it means it came from a web server application. So I'm going to tell my computer to record everything to and from port 80 over my wireless LAN. So now it's what we say capturing. My computer, it's not showing anything. Any data being sent and received by my computer will be captured by this program and saved in a file. And then we'll look at those packets. Let's now look at the web browser and visit our website. Just an example website. So I type in the URL and I press enter. That should trigger my browser to send a request. Let's hope so. There we go. So what happened is that my browser sent a request to the web server. The server has a domain name sandylands.info, and it was a request for a page index.html under the directory test. And what came back was the contents of index.html, and that is shown or displayed on the web browser here. It's just a test web page. If we look at the source of that web page, we'll see the HTML. It's just you've created, or you're creating HTML, I think, in some lab class. If not now, then soon. It's just the contents of the index.html page. It was received by my web browser. The web browser reads the HTML, recognises what it needs to do with the title, display at the top of the browser, and the contents displayed in the main screen. Now let's go back to my other software, which was recording everything that was sent. So my computer had to send and receive packets for that to work. This software recorded those. Let's stop the recording. And now I'm going to open that file in another piece of software. So the file web1.cap. This software is called Wireshark. I'll open the file and then explain. Web1 is the file we just created. This software displays those packets that I captured. My computer sent packets over the internet and received them. The first program captured those packets, recorded them. This software just displays them in some nice graphical interface. I'll first find the packets and then explain what it's showing us. Many packets. Let's try something different. Maybe not. We captured many packets. I just need to find the packets that I sent, or the ones we're interested in. It's harder than I expected, or harder than this morning. There we go. My address 10.10.3 okay. So let's explain what we see here. My computer sent many packets. I just want to show you two of them. The two packets. The first one is the packet that my computer sent to the web server, requesting the page. The second packet is what comes from the web server, which contains the web page. I had to find them because there are many others. The first one, the one highlighted in orange here, is the request to the web server. How do I know? The source and destination address. The source address is my laptop. So what this row shows, one packet sent at time 38.8 seconds after I started the program, coming from this computer, 10.10.3.239, going to this destination computer on the internet, 125.25.29.19, and using the protocol HTTP, which we know is the protocol for web browsing. And the summary information says that that packet contained this information, get/test/index.html, because what I typed in the browser was a request for that test index.html page. And the third packet here ignore the black one, is the response. The source is this computer, destination is 10.10.3.239, this computer, my laptop. So we send a request and then we receive a response. And this is also using HTTP, and it contains some status message, 200 OK. This program just shows us the packets that were captured, that were sent and received. This view is just a summary of the packets. If we select one, the orange one here, here we see all the details of the contents of those packets, of that one packet. Let's look at the details. And explain them. So this is the packet that has been received by my laptop. So it's come in here. I send a request out. The first one, 788. 948 is the one that comes back. It comes into my laptop. My LAN card receives it, my wireless LAN card, sends it to my operating system, and this or the capture software took a record or a copy of that and is displayed here. So what was received? Some data was received. Let's draw it over here. The data, well, what is the data? Let's have a look. This is the application data that was sent by the web server. We see it's the HTML page. This is the actual data that my computer received in that packet. It's just the HTML that the web server sent to my computer. So the data in this instance is some web page. That's what I requested. I send a request to the server for a web page. The server sends it back as data. That's good. But there's all this other stuff, which is in fact the headers of the different protocols which we use to transfer that data. That data didn't magically arrive. What happened is we used HTTP to send a request and send the response. We used TCP to deliver that between applications and to check that there were no errors. We used IP to deliver it across the internet, and Ethernet to deliver it across that last link into my computer. So each of those protocols, if you remember from yesterday, we take the data, each layer adds on a header and sends the result to the next layer, adds on the header to the next layer until we get that final sequence of bits which are transmitted across the link. Similar when we receive a signal, convert it back to bits, pass that up through the layers until we get the final piece of data, our web page. This software shows us those headers. We minimize, we can see the HTTP header. So this is the header that HTTP added. It contains some status code. Everything was OK. Remember, this is the packet the server sent to my browser. I requested a page. The server sends back, OK, your request was OK. I have the page. The page is included as the data. But it also includes some other useful information from my browser. The date and time. Some identifier of who the server is or what software the server is running, what operating system is running. Some information about when the page was last changed. Some encoding the length of the data and many other things that are useful sometimes for the web browser to communicate with the web server. So that's the HTTP header. How big is the HTTP message? If we select one part of that message. This part summarises down the bottom. Stay there. Summarises down the bottom. This is 17 bytes. That's just one part of the header. This one is 37 bytes. And that's 32 bytes, and so on. So that header, the total size, 455 bytes. And that includes, in this case, what have we got for data? The data was 93 bytes in this example. And HTTP 455 bytes. When we did that calculation yesterday, I made up some different numbers, like 10,000 bytes or 1,000 bytes for the data, so many bytes for the header. Here are the real numbers in this instance. The transport layer used in this case is TCP. That's the transport protocol. The application protocol, HTTP, took some data, added the header. TCP was then used, and there's also a TCP header. Again, contains different fields of information. Two of them that we notice or know something about at least: the source and destination port. These port numbers, remember from addresses, port numbers indicate the applications that are communicating. On my laptop, this computer, I was running a web browsing application, and the server was running a web server application. The web server, the packet we're looking at here, came from the web server. The source is port 80. The web server on this computer is identified by the port number 80. My browser, which is the destination of this data, has port number 52965. So this data, it comes into my computer. The destination port number of 52965 is going to tell my computer to send it to the web browser application on my computer. Not to the instant messaging application, not to Skype, not to some other application, but to the web browser. That's what the port number is used for. There is some other information also in the TCP header. TCP header is 32 bytes in this example. Next is the network layer header, the internet protocol. 20 bytes in length. So that includes things like what version of IP is being used, IP version 4, the length of the header, 20 bytes, and again, things we recognise, the source IP address and the destination IP address. I won't write them in full. Included in the IP header is the source IP and destination IP. That is, the source is the server 125.25.2919. Destination was my computer 10.10.3.239. This IP packet was created by the source computer here. destination address was 10.10.3.239. That was sent out. We think of it's sent across the internet. And all the devices which connect our path from source to destination receive that, look at the destination, and try to deliver it to the correct destination based on the source, based on the destination address. So the source and destination are included in here. And the last header is the data link layer, the Ethernet header. (14 bytes). Contains the hardware addresses. Source hardware address, destination hardware address, HW, shown here. These hexadecimal values are the hardware addresses. That is an illustration of the packet that my laptop received. It received it across the wireless link, in fact. It's not a wired link, it's a wired wireless link. It received it from the computer beforehand. It came from the device with hardware address, this one, 0050, that's the source hardware, and my laptop has this hardware address, 0026, and so on. It arrived at my computer. My computer received this, checked, okay, I am the destination of this Ethernet frame. The destination hardware address matches my hardware address. Therefore, my computer, or the LAN card, wireless LAN card, removed the Ethernet header and sent all of this to the IP software in my computer. That is my operating system. My OS, the software for the Internet Protocol in my operating system, checks everything, looked at the destination IP address. It matched my computer's IP address. Therefore, this packet must be destined to my computer. Eventually removes the IP header and sends everything else up to the transport layer inside my computer. TCP does its job, checks everything, sees that the destination is 52965, that's the port number. So if we draw what's happening in my computer, the LAN card, or the wireless LAN card, receives some signal, checked the destination, sent what was received to the operating system, and in fact inside the operating system specifically to the IP software, the Internet Protocol. That sent also in the operating system to TCP, this portion. TCP looks at the destination address, the destination port number 52965, removes the header and sends this to the application. It knows to send to the web browser software on my computer because of the port number. Destination 52965. My browser is using port number 52965. Therefore, the operating system knows to deliver this to the web browser. Web browser receives it, checks, looks at the HTTP header, everything's okay, removes the header, and then the web browser processes the data. In terms of processing the data, in this case it looks at the HTML and displays something on the screen. This is a test page. Remember, the data shown here is just the HTML. This is the data. This was processed by the web browser. What the web browser does is reads the HTML, puts the title on your browser as test, and puts on the screen, this is a test for ITS323. And that's completed the data transfer. So that's a real example of how the data flows through the protocol stack. We're seeing it coming up, being received. The headers are removed until the data is processed. Of course, at the source, we start with the data, add the headers, it flows down, and then is transmitted. It is actually more complex because it also happens at these intermediate devices. This one receives, may process some part of the packet, and then modify it, send it on, send it on, send it on, until we get to the destination. Note in this case, look at the overhead. To send 93 bytes of data, that's all the real data we wanted to transmit. All I wanted was to get this 93 bytes of HTML from source to destination. We've got this 455 plus 32 plus 20 plus 14 bytes of header. So there's more than 500 bytes of header just to send 100 bytes of data. So it's in fact quite inefficient to deliver that across the network. But in practice, not a big problem because the speed to send that is quite fast. The data rate is fast. Any questions about that? This is just another example of what we went through yesterday. Last lecture before a quiz next week. So we try to take in some of these examples, and especially when we go through some calculations today. Now that's one example showing web browsing. The next thing, or the thing that we finished on yesterday, was about performance. That is, we mentioned something called bandwidth. We didn't say much about it. And then we said data rate is a key performance metric, and also throughput, and then delay. Let's continue with them. Of course, if I gave you that information in the quiz next week, then you could calculate the overhead. You may calculate the efficiency. When we say, in this simple case, what's the overhead and what's the real data, what's the efficiency, we care about the real data, 93 bytes, versus the rest of the bits that we need to send. That's the overhead. We cannot avoid this. We need all this information for the protocols to work. So we cannot get rid of this. But it is an overhead from the user's perspective. How do we measure the performance of a link or a network? When you graduate, you go get a job, and it's your job to advise your company on what network you should build. What technologies should you buy to build your new network? Well, some of the things that you need to consider are, of course, performance. And these are some of the metrics, some of the ways we measure performance. The other thing you need to consider, of course, is cost. Data rate, the maximum speed we can send bits across some link or channel or network, measured in bits per second. Throughput, the speed at which the real data is successfully delivered to the destination. There's a difference here. If we need to transmit this packet, we need to transmit all bits. If we have a data rate of our link of 1 megabit per second, 1 million bits per second, And we have to transmit all these bits at that speed. The throughput is the rate at which the useful data gets delivered to the destination. So throughput, we only count the real data that's of interest to the user. Let's give an example of those two, of data rate and throughput, using our wireless LAN. We don't need this. Let me just check computer. I'm going to download a file from the ICT server, from some computer in the network, to my laptop. And we're going to measure how fast it's downloaded. Remember the file name. Remember, when you type into your browser a domain name, ict.sit, so on, it actually maps to some IP address. Your computer doesn't use the domain name to send a packet, it uses the IP address. So there's some mapping. Given a domain name, what is the corresponding IP address? So in fact, you don't have to type in the domain name, you can type in the IP address directly. Only if you know the IP address, which I do in this case. It's the IP address of the ICT server. I'm going to download this file. It's a large file on the server. And okay, it's 10 megabytes. It averaged at 983 kilobytes per second. That's the speed at which I receive that file. Let's make note. Where's my pen? Let's check. Now let's look at the data rate of my wireless LAN. I can type. So I downloaded that file via my wireless LAN link. This program just reports some statistics or some configuration of my wireless LAN card. It says the bit rate is 54 megabits per second. That's the data rate. That's the maximum speed I can send data across my wireless link. But when I downloaded the file, the speed at which the data was received was 983 kilobytes per second. It was uppercase B here. Kilobytes per second, 983,000 bytes per second, but the data rate is 54 million bits per second. Convert this to bits, what do we get? Approximately. Well, it's approximately 1,000 times by 8 to convert bytes to bits, so we get approximately 8,000 kilobytes, kilobits per second now. All I did is converted bytes to bits. Multiply this by 8, about. Or 8 megabits per second. 8,000 kilobits per second is 8 megabits per second. That's my throughput. of transferring that file, I could receive the data at 8 million bits per second. But my data rate was 54 million bits per second. Why didn't I get a higher throughput? Well, there are many things that my wireless link was doing which wasn't transmitting or wasn't receiving data. There were overheads. The data that we count in that 8 megabits per second only counts this portion. It doesn't count all of these headers that we need to transmit. In addition, in a wireless LAN it's more complex because in a wireless LAN there may be someone else transmitting at the same time. And it may mean that I have to retransmit some of the packets. And that means that even though I'm sending at 54 million bits per second over the wireless link, in total only 8 megabits per second is the sending of the real data. This is what we care about as users. When you download a file, this is an indicator of the speed at which you can download that. This is an indicator of the maximum speed that your link can transmit bits. So in fact we're getting what, 1/7 of the maximum capacity, which is quite inefficient. And wireless LAN and wireless transmissions generally are inefficient. That is, my maximum speed is 54, but I only use 8 out of that 54. I'd like to be more efficient than that if possible. So, most technologies, LANs, wide area networks, the data rate or the bit rate is a characteristic of that technology. When you buy a wireless LAN card, you know the maximum data rate it supports. 54 megabits per second, my laptop does. But that's not a measure of the throughput. The throughput depends upon many different factors. It depends upon the size of the headers, the size of the data, whether someone else is transmitting at the same time. So there are many factors that make it hard to know in advance what the throughput will be. So when you buy your wireless LAN card, the marketing material says the data rate. But you will know in the future that that doesn't mean that's how fast you'll be able to download files. That's the throughput. And the throughput may vary under different conditions. I run the test again, download the same file. 1.3 megabytes per second. Before I had 1 megabyte per second. Same file, same amount of data, same link, same data rate, different throughput. Just because of different conditions, maybe someone else is not transmitting in the vicinity in this case. So the throughput is harder to know in advance. So when you buy technology, you care about the data rate, because that's usually known in advance. But more importantly, you care about the throughput. But you cannot predict the throughput in some cases. So you're just stuck with the data rate. And we can measure some efficiency. It's simply in this case, the efficiency of using that link, we're using 8 out of 54. Which is whatever it is as a percentage. That's the efficiency of using that link. Any questions on how the throughput relates to the data rate? That's an important thing. There are two measures of speed. One measures how fast we can transmit any bits. One measures how fast we can deliver the real data. If you have no questions, then let's do an example. I'll let you do an example. A simple case or a simple scenario. We have 3 computers, 2 links, so it's a very simple network. Computer A has a very large file it wants to send to computer C. What it does, it sends them over the link to computer B. Whenever computer B receives the packets containing that file, it immediately sends them to computer C. What computer A is going to do is, let's say it's got a very large file, 1 gigabyte. Instead of sending it all at once, it sends it in small packets, 1,000 bytes at a time. Sends the first 1,000 bytes, and then the second 1,000 bytes, and so on. Keep sending small chunks of the file, one at a time. As computer B receives a packet, it immediately sends onto computer C. And C receives them and gets the file eventually. There's no delay at computer B. It's a very fast device. It receives and immediately sends. So it's as if something comes in and immediately goes out. The data rate of the first link is 10 megabits per second. The data rate of the second link is 100 megabits per second. There's an overhead. So we have 1,000 bytes of data. On top of that, we add some headers. I'm not going to say what they are, just say the total of the overhead is 60 bytes. What's the maximum throughput we can achieve? Calculate that for the next 5 minutes. I'll come around and look at your answers. We want to know what's the throughput that we achieve in this scenario. We're sending our file from A to C. How fast is the real data being delivered? So I want to see pens, pencils, and a piece of paper in front of everyone and trying to calculate. Or use your computer, that's okay. The answer for this one's not in the lecture notes, or it's not in the handouts. Anyone got an answer? We have the size of the real data, you have the overhead, you know the data rate, what's the throughput? Okay. Answers? Some people are good at copying down the question, but that won't get you far. You need to compare the real data versus the total amount of data that we need to send. Okay, tell me when you're sure. If you're struggling, then just focus on the first link for now. Ignore the second link. Another hint to make it easier, maybe you could try to calculate the efficiency first. I'm not sure. For some people that may be easy to look from that perspective. What's the efficiency in terms of how much time do we spend sending real data versus the total amount of data? People are getting close. Did you get that by yourself? We have an answer. A correct answer. Anyone else? Okay, let's explain. All right, we have a correct answer, so let's try and explain how he arrived at that. Let's just focus on the first link, and then we'll explain the second link. We're sending packets of 1,000 bytes. It's as if we have a large file to send, so we send one packet, immediately after another one, and let's say forever keep sending packets. Let's just focus on one packet. We send 1,000 bytes of real data, but in fact every time we want to send 1,000 bytes of real data, we actually have to transmit an extra 60 bytes. Think of it as the application generates 1,000 bytes here. It goes through the different protocols. What comes out here is 1,060 bytes. That is, the protocols add an additional overhead of 60 bytes. So we in fact have to transmit 1,060 bytes. We transmit over the link, and the way the first answer was calculated, okay, how long does it take to transmit 1,060 bytes? Well, first let's convert it to bits, times by 8. What do we get? 8480 bits. Just multiply by 8 bytes to bits. Now the question is, how long to transmit that over the link? Well, we're sending 10 million bits per second. We want to send 8480 bits, so the time is simply the total number of bits divided by 10 million. 10 by 10 to the 6. This is bits divided by bits per second. Now remember, be careful with the units when you're dividing different quantities. One way to make sure what the resulting units will be to divide the units. bits divided by bits per second, bits divided by bits per second is B over B times by 1 over 1 over S. Bits, B times 1. Bits per second, B times 1 over S. Just thinking of the units. They cancel out or become 1. So it becomes 1 over S, which equals S. In other words, bits divided by bits per second gives us the units of seconds. That's just to work out the units. This divided by 10 is 848 microseconds. But if we divide something by 10 to the 6, it will give us micro. So 848 microseconds. That's the time to transmit one packet. What's the throughput across that link? Well, the throughput is the rate at which we receive the real data. We're sending 1,000 bytes of real data, and it takes 848 microseconds. And then we send another 1,000 bytes of real data, because we've got a large file with many packets to send. We send 1,000 bytes, it takes 848 microseconds for that first one, then another 1,000 bytes, another 848 microseconds, and we do that continuously. Let's say we have many packets to send. So in fact, we're sending 1,000 bytes of real data. Make it simpler, 8,000 bits. 8,000 bits of real data every 848 microseconds. And that gives us, the answer was at the back. Who had the answer? Wake up. Just because you got the answer. What was the answer? What was the answer? 9433 something. Something. Bits per second. 94333. 9,400,000 bits per second, which is approximately 9.4 megabits per second. Our data rate of our link was 10 megabits per second. Our throughput across that link is 9.4 megabits per second. That makes sense because for every 1,000 bytes that we want to send, every 1,000 bytes of real data, we actually have to send 1,060. I want to send 1,000 of real data, I transmit 1,060. There's 60 overhead, which is an efficiency of 94.3%. That divided by that is 0.943. If we've got an efficiency in this case of 94.3% and we've got a 10 megabit per second link, that is, we're using 94.3% of this, which is 9.43 megabits per second. I've rounded some parts there. So there are two different approaches to getting that same number. Simply look at the real data divided by the total data to give us some efficiency, and then from the data rate give us the throughput, or look at the time to transmit the total data and then the real data divided by that time gives us the same number. It's the same value. That's for the first link. We get 9.4 megabits per second. What about from A to C across the network? It's the same. Why? Assuming we said B just receives the data and sends on immediately. In real life there may be some delay there, but we say that's very fast speed. think, if I'm sending data continuously onto a link that supports 10 megabits per second, and then this one sends it onto a link that supports 100 megabits per second, B is never going to send faster than at 10 megabits per second. A is sending at a maximum of 10 megabits per second, therefore B is receiving at 10 megabits per second. B's got nothing to send at a faster rate than 10 megabits per second. So even though B can send at 100 megabits per second, and it will send, and then for some period of time it will do nothing because it's got no more to send. On average, B will be sending at a throughput which is the same as what A is obtaining over the first link. That is, the throughput from A to C is 9.4 megabits per second. Think of a water flow through pipes. You have a narrow pipe which allows so much water per time through. And then it reaches a big pipe which allows much more water through time to flow through that pipe. It doesn't get any faster through the big pipe. The speed at which the water travels through the big pipe is the same as what arrives from the small pipe. We cannot send any faster over a long period of time from here to here. We're limited by the rate here. And you can generalize that to say across a network of links, a path of multiple links, the data rate that you can achieve is the minimum of the data rates of each of the links. Data rate of 10, data rate of 100. From A to C, we cannot get more than 10, the minimum of these two. That's a little bit more involved than the simple or initial calculation of throughput. The throughput, real data as a ratio of the total data, gives us some efficiency of how we use the data rate, and that delivers the throughput. We have 10 minutes left. Let's give another example. In preparation for our quiz. An example on delay. Delay consists of 4 components. We can break the delay across a network into 4 components. The time to transmit. From the source computer we have some data, some bits to send. The data rate limits the speed at which we can transmit that data. We saw if we wanted to transmit 8,480 bits at a data rate of 10 megabits per second, that'll take us 848 microseconds to transmit that data. Because we send 1 bit at a time. Send the first bit, the second bit, and so on. Total time to transmit all bits, 848 microseconds. That's what we call the transmission rate. A transmission delay, sorry. Let's consider an example. Here's our satellite network. We have a satellite up in space and some ground station here in Thailand and another ground station somewhere in Australia. And what we do with this satellite communications, let's say we have a computer here, wants to communicate with a computer here. It sends up to the satellite. The satellite takes what was received and simply sends it down to the receiving ground station. Let's go through our example. The links, so these are two links. One link that goes up and one goes down, the uplink and the downlink. And let's say they have the same data rates. What have we got? 1 megabit per second. Keep it simple. We have data to send, and let's say we have, again, 1,000 bytes. What we do, so we have a packet of 1,000 bytes. Forget about overheads when we're looking at delay here. Just ignore overheads. What we do is we transmit this 1,000 bytes up to the satellite. When it's fully received, the satellite does a little bit of processing and then sends it down to the receiving ground station. So the uplink has some transmission delay. The transmission delay is simply the data size divided by the data rate. That's what we did over there. 8480 bits, data size divided by data rate, 10 megabits per second. Our case, the uplink, 1,000 bytes divided by 1 megabit per second is what? 0.8? No, it's not. It's 8 milliseconds. You can do the conversions. 1,000 bytes, 8,000 bits divided by 1 million bits per second is 8 milliseconds. That's the transmission delay up to the satellite. But in fact, once the satellite receives that, in this scenario, it needs to transmit down to the ground station. So the downlink transmission delay is 1,000 bytes divided by 1 megabit per second down. It's the same in this case, just in this example. So I'll go through some calculations quickly here. It takes 8 milliseconds to transmit the data out of the ground station here, and another 8 milliseconds for the satellite to transmit the data down to the ground station here. In a network, each computer takes some time for that data to pass through the computer. The stack, the application, the operating system, the hardware, it takes some time to do that. We say that's the processing delay. That is, my application presses send. And then for my computer to process that, to create the data, create the packets, and then transmit, there's some delay incurred there, the processing delay. In many cases, that's very small. It depends upon the speed of your computer. How long does it take for my computer to process 1,000 bytes of data? It could be nanoseconds, microseconds. I don't know. It's very hard to calculate in advance. In many cases, it's very small compared to other delays. And sometimes cases, we just ignore it because it's so small. In this example, let's say the processing delay of my computer here is small. It's 0. Same here. But the processing delay of our satellite, let's give it some value just to introduce some value. 4 milliseconds. That is, the satellite receives the packet. It's a computer. There's a computer on board. It processes it, looks at it, does some things, and then starts to transmit. That processing, I'm just going to give it a value of 4 milliseconds. So in fact, now, the time to get our data from here to here, we have 8 milliseconds transmission, 4 milliseconds processing, 8 milliseconds transmission. But when we transmit, the signal needs to propagate to the satellite. We send some signal, some electromagnetic signal, and as we said yesterday, a waveform propagates. The further the distance, the longer it takes to propagate. How far from the ground to a satellite? Well, some satellites, geostationary satellites, are about 36,000 kilometres away. Propagation delay is distance in metres divided by speed in metres per second. We've got 36,000 kilometres for our signal to propagate up to the satellite. The speed at which it propagates, we say, is the speed of light. (3 × 10⁸ metres per second. So in space, our signal can get very close to the speed of light. It just propagates up there, and that gives us 36,000 kilometres divided by 3 × 10⁸ is 120 milliseconds. So what happens? I'm sitting at a computer at this ground station. I press send. My computer does some processing, but I'm saying that processing is very small, 0 in this case. Then my computer takes that 1,000 bytes and transmit 1 bit, the 2nd bit, the 3rd bit, and then the 8,000th bit. 8,000 bits it transmits. The time it takes to transmit 1,000 bytes is 8 milliseconds. But the signal, as it's transmitted, it propagates 36,000 kilometres, some waveform. At the speed of light, travelling 36,000 kilometres takes 120 milliseconds. So 8 milliseconds to transmit plus 120 milliseconds to propagate, to get there. That's the travel time of that signal. Once everything's arrived, the satellite processes that piece of data for 4 milliseconds and transmits down to the ground station at the receiver. It transmits at the same data rate, the same amount of data, and therefore a transmission delay on the downlink of 8 milliseconds, and it also must propagate. Same distance, same speed of light, that doesn't change. Another 128 milliseconds propagating down. We receive it, it processes it, but the processing time is 0. Therefore, the total delay, 0 plus 8 to transmit, plus 120 to get there, plus 4 to process, another 8 to transmit down, another 120 to get down, and 0 here, which is what, 240, 260, is it? Just the summation of those values. 8 milliseconds transmission, 120 propagation, 4 of processing, 8 of transmission down, and 120 of propagation down. Gives us 260 milliseconds. I press send. It's received here 260 milliseconds later. A quick example, that one's in the handouts, but illustrates 3 of the main components of delay. Transmission depends upon the data rate and the size of the data. Propagation depends upon the physical distance and the speed at which signals are sent. Usually the speed of light, sometimes, or in practice, a little bit less. Processing is the time for that computing device to process that data. Sometimes it's very small, sometimes it can be significant, or 4 milliseconds. It's hard to calculate, so often we just give a number, or some number is given. We do not have a formula to calculate processing delay. Last one, queuing delay. Sometimes there are many packets arriving in this satellite from different ground stations, all at the same time. 3 different ground stations send up to the satellite. It receives 3 packets. It can only transmit 1 at a time. Those second 2 packets must wait in a queue, and therefore they incur some queuing delay. So a 4th component, which is not in this example, is queuing delay. Make sure you know how to calculate transmission delay, propagation delay, and you know that the total delay is really the sum of all the component delays. Delay is additive. You just add up all the components. And treat each link separately. If this link had a data rate of 10 megabits per second, the downlink transmission time would be 0.8 milliseconds. Uplink 8, downlink 0.8, if this was 10 megabits per second. So some links may be different, like in the example over there. We've run out of time today, but that I think gets us very close to the end. What we'll do next week is have a quick quiz on the things we know, mainly about protocol architectures, that is about the 5-layer stack, the very basics of what the layers involve, or maybe, I mean, you should know that IP, the Internet Protocol, is part of the network layer. But many of those other protocols we've mentioned and we haven't explained, well, they're not so important. And very basics of how do you calculate delay or perhaps throughput. What's the difference between data rate and throughput? And then we'll summarise on this and move on to the next topic of data transmission. So enough for today. We'll see you next week. And next week